Hey guys, welcome back to Gluten-Free Learning. So today we're going to be looking at some beam theory and the Euler-Bernoulli equation. So this is basically kind of a little segue into looking at beams for finite element methods, because previously, up until now, we've always had either springs, dealing with spring systems with axial forces, developing our stiffness matrix K, and analyzing the system in one dimensions. And then we looked at truss systems where we had two-dimensional systems, more than one or two nodes, and we've had nodal forces. And then we'd also get our stiffness matrix K, and that was in the form of, AE over L or whatever. So now when we're dealing with beams, it's a little bit different. We're still going to have our members and our nodes, say for example node 1 and 2. And now we can actually have, we can look at span loads of submagnitude P by themselves, or we can throw in, a uniformly distributed load or some combination of the two. Right? Because with trusses, for the purposes of finite element methods, they don't resist any bending moment, and springs, they don't resist any bending moment or vertical displacements. But for beams, they do resist bending, and there's going to be some kind of rotation. There's going to be a degree of freedom rotation, and it's called phi. So that's kind of the idea behind beams. Now, I'm going to go through a little bit of beam theory so we can get the notation down for when I go through an example later and find stiffness matrices. Alright, so basically that's the only difference we have now. We're going to have bending resistance, and then we're going to have angle of rotation, degree of freedom called phi, at each of the nodes as well. So, okay, say we're given some beam element looking like this, and we know the neutral axis goes through the middle. The neutral axis means that there's no stress. So if we're drawing our stress-strain diagram, or our stress relationship, we can see that it crosses over the neutral axis, and at this point at the neutral axis, that is where the stress converts from tension to compression. Right, so the top of the beam will be in compression when we're under some load. Say for example we got a uniformly distributed load, Wx. This beam is going to deform, and our stress at the top is going to be in compression, and the bottom will be in tension. And as it crosses over the neutral axis, at this point it will be zero. So if we draw out what the deformed shape is going to look like. Now this is going to be a little exaggerated obviously, but our neutral axes will have deformed, and our beam will also deform. So this is the deformed shape of the beam. Our neutral axis deforms with the beam, and at the neutral axis we still have the stress crossing over from compression to tension, and it's going to be zero at the neutral axis, which is why it's called the neutral axis. Call it A, B, C, and D. So if we have this section A, B, C, D, and on our normal shape, these are right angles, A, B, C, and D, the same section will have deformed, so there is still a right angle where line AC crosses over the neutral axis. Because, like I said before, the neutral axis will deform with the beam, and the section remains plane, meaning that lines AB and lines AD will still remain perpendicular to the neutral axis. So the section does not deform. Alright, so looking at our shape, taking our section, looking at our section here, with our uniformly distributed load, Wx, A, B, C, D. We know that this length is going to be some length. Let's call it dx, some unknown. And we're going to have our shear force V of x, and also a bending moment at this point. Call it M of x. Our shear force on this side will be V of x plus dV. It'll be some small change in our shear, and our moment will be our m of x plus dm, some small change in m, because Just like in your structural analysis course, if you sum your forces and if you take a section in your member and then you sum your forces, there's going to be some small change as you go, because there's uniformly distributed load. You have some small change dx, so there will be some small change in your bending moment and also in your shear force. So if we sum our forces, the shear forces, we will get our uniformly distributed load Wx equals minus dV by dx. Right, so that's our first important relationship that we need to keep in mind. Sum our moments at our section, we get V of x equals dm of x, and that's our second important relationship, okay? Now you likely will have seen these relationships before in your early structural analysis course or your mechanics of materials course, but I'm just doing a general overview of some beam theory, so when we go into finite element methods, you kind of have a better understanding of where I'm going to get some notations from. Alright, so looking back at our deformed beam, our deformed shape, this will be due to some uniformly distributed load or some point load or whatever. That doesn't matter. What matters is, okay, so along any point on the neutral axis in our deformed beam, let's pick a point right here. Right, we're going to have some V of x, meaning we're going to have some transverse displacement. Some transverse displacement going in the y direction. And also we're going to have our radius from some point, and that's going to be equal to rho. So that's our radius of curvature at some imaginary point connecting our neutral axes to this point. And how to calculate that is not that important in this course. You will have learned how to do that in your mechanics of materials or mechanics of solid course. So for now, just know that it exists and what it's called. Right, so that is rho. So now at any point we've got our transverse displacement, we've got our rho, and the rho should be constant along the neutral axis given a deformed shape. So the rho will be constant. And the transverse displacement, that will not be constant. That changes with x. That is variable. And also, at this point, we're going to have a local coordinate system. So we have a y and our x. That's our global coordinate system. And let's just local coordinate system here. X prime and y prime. So those are local. Those are for every point, at any point along our beam. And then drawing a tangent at our point, we got an angle. We've created an angle at the point, right? That angle, at any point along our neutral axis, we're going to call that phi. So what does phi mean? Well, first let's take the tan of phi. So we know the tan of phi is going to be equal to phi because we're dealing with really small displacements, really small change in v over the change in x. dv by dx equals phi, right? So rise over run, because we're going to have some small change in v, vertical, and we're going to have some small change in our x, distance. And because they're very small, put it in your calculator, very small angles, when you take the tan of it, is going to equal the angle itself. So we're going to say phi is equal to dv by dx, and that equals our change in transverse displacement per unit length. Right, so that's going to be one of the more important relationships when we're dealing with the beam theory. Phi equals dv by dx. That is what we're going to basically use to set up our equation with our finite element method problems. So if you take anything from this video, just know that phi equals dv by dx and understand that it's the change in transverse displacement, the vertical per unit length. Right, so that is the main thing that we're trying to get home. That's the message we're trying to hit home run here, okay? So remember, just make sure you know that if you're taking anything from this video. And also let's define K to be the curvature. And you would know from your mechanics of solids or mechanics of materials courses, or maybe even your structural analysis course, that the curvature, that equals our M over EI. Alright, so let's just call this equation 1. And let's look back at our phi. Let's call this relationship here equation 2. And we also know that K, curvature, equals d squared v over dx. Right, so the change in double derivative of the displacement per unit length. Let's call this equation 3. Now these would have been from your structural analysis course again, so just know these relationships, understand them, and then we can apply them to our beam theory. So looking at equations 3 and 1, if we equate equations 3 and 1, then we can get this relationship. We got d squared v by dx squared. So that was our equation 3. And we set that equal to equation 1 because they both equal k, right? We got the k of the curvature, then we got the k. We also know that it equals the double derivative of the displacement over dx squared. Right, so we get the following relationship. D squared v over dx squared. And then remember from before, we defined our load w of x up here and our v of x from taking a section and summing our forces of our beam. So that still applies here. Can't forget about that relationship. So v, or w of x, is equal to minus dv by dx, and also our v of x equals this. Okay, yeah, minus, yeah, we're good. So using this relationship between these two functions, we can say our w of x equals minus d squared m over dx squared. And this, that's our equation 4. And our d squared v over dx squared equals m over ei will be equation 5. So now if we substitute 4 and 5, we get the relationship of minus w, the relationship of the beam. This is basically the beam theory. And then using the Euler equation, if Euler's theory says if w equals 0, we have no span forces. We have no forces on the span. And you'll see later on when we develop our stiffness matrix and our methods to use the fixed end moments, how this comes into play and how this is solved using the beam theory and the Euler-Bernoulli equation. So this will say that we have only node forces. So if w equals 0, then we've got 0 equals, so we have 0 equals ei times d squared v over dx squared, and this is the Euler-Bernoulli relationship for beam theory. And this is really important in finite element methods because it relates the deformation, it relates the moments and the shear, and also the beam curvature with the material properties. So this is important for what we're doing in finite element methods because we are now going to be having our moments resisting and our angular rotation at each of the nodes, as well as forces on the nodes. Because before we only had displacements as our degrees of freedom, but now we're going to be looking at our bending. So that's the most important thing about the beam theory, is that we're going to be applying that to our finite element methods problems and our systems by adding another degree of freedom for resisting the bending and creating some curvature at nodes. So in my next video we're going to look at an example on how we apply this beam theory to systems of equations in finite element methods. So remember that our change in transverse displacement per unit length is equal to phi. This is important, right? So this is going to be basically the new unknown. The new degree of freedom is going to be our phi for our systems of linear equations and our beam in our finite element methods problems. So that was a little bit of beam theory. Thanks for watching my videos. If you like, please subscribe to my channel and check out my website, link in the description. There will be more to come, so thanks for watching.